Welcome back! In our first lecture, we introduced the concept of medical imaging as a means to extend our natural vision, to see inside the human body, guide care, and save lives. We then discussed the structure of this course and touched on some of the tools we'll use along the way, such as MATLAB. Now we're ready to take the next step. Today I start teaching on the foundation of this course. This part is crucial because it gives you the knowledge and skills you need to truly understand the medical imaging systems we'll explore later on. Systems for CT, MRI, PET, and more. You can also think of this foundation as the main framework. Once you have it, you'll be ready to make sense of the advanced imaging methods and technologies that are transforming modern healthcare. Let's get started. We are right on schedule in our journey through this material. If you've had a chance to look over the reading materials for today's lecture, that's great. It will make it easier to connect the ideas we cover. If not, that's fine too. I encourage you to follow along closely and take time afterward to review the main points. Consistently reinforcing concepts as you go will help you develop a stronger and more intuitive grasp, especially as the material becomes more mathematically detailed. Now that we've set the stage, let's learn one of the most central ideas in this foundation, what we mean by a system. This concept is at the heart of all imaging technologies we'll study. A system, at its core, is a set of components that work together to produce a specific result. In medical imaging, understanding systems helps us see how different parts, from hardware to algorithms, combine to generate the images we rely on in healthcare. Today's lecture is designed to break this down clearly. We'll begin by exploring general systems, and then we'll narrow our focus to linear systems, those that behave in predictable, mathematically straightforward ways. These systems follow two key principles, additivity and homogeneity. Together, these form what's called the superposition principle, which we'll explore in detail. Finally, we'll briefly look at non-linear systems, those that don't follow these linear rules, so you can have a big picture of the full range of systems and put medical imaging in perspective. Let's get started. Now that we've introduced the idea of systems, let's take a moment to connect it to something you're probably more familiar with, functions. A function, as you know from mathematics, is a rule that links each input from one set, the domain, to exactly one output in another set, the range. It's a clear, well-defined relationship between input and output. A system works in much the same way, but often in a more complex and dynamic context. A system takes an input, processes it through a group of interconnected elements, and produces an output. These elements could represent anything, parts of a mechanical device, components of a physiological system in the body, or even elements of a social network. What matters is that they work together as a whole to produce a result. Both functions and systems help us describe how inputs lead to outputs. And in medical imaging, defining these relationships precisely is what allows us to design, analyze, and improve the technologies we rely on in healthcare. So as we move forward, keep this comparison in mind. It's a helpful way to understand how systems operate, and it will give us a basis for exploring both linear and nonlinear systems in more depth. Let's continue building on that comparison between functions and systems by looking at a simple example of how a function works. Imagine you start with a value from the domain, let's say a number, and apply the function. That function maps your input to a specific output in the range. Just like in a system, there's a clear relationship between what goes in and what comes out. In my slides, you'll notice I use icons to help highlight what's most important. When you see a red diamond, that marks a key point, something I really want you to remember. A green disc points to interesting material that's a bit beyond what you absolutely need for engineering purposes, but could be valuable if you're curious to go deeper. We're not aiming to become mathematicians here, but having a solid grasp of these basic ideas will help you understand medical imaging systems at a deeper level, and that's what we're after. So far, we've talked about functions as mappings between inputs and outputs. Let's take that a little further by looking at some examples. Functions come in many forms. You're probably familiar with linear functions, where the relationship between input and output is straightforward, just a straight line when you plot it. Then there are sinusoidal functions like sines and cosines, which you've seen in trigonometry and signal processing. And if you've explored beyond the basics, you might have come across more complex structures like those defined recursively in fractal geometry. Fractals create fascinating patterns that repeat at every scale, and while they're not central to our work in medical imaging, they're a beautiful example of how functions can model complexity in the world. For our purposes, though, you don't need to go deep into fractals or other advanced forms. What's most important is that you feel comfortable with the idea of a function and its basic properties. So far, we've talked about functions and how they map inputs to outputs, and we've seen some familiar examples. Now let's look at a mathematical tool that helps us work with functions in a very practical way, the Taylor expansion. The Taylor expansion is a method for approximating a smooth, well-behaved function using a sum of simpler terms. It starts with a constant, the value of the function at a specific point, then adds a linear term that depends on the first derivative, and further a quadratic term based on the second derivative, and so on. Each term you add improves the approximation if certain conditions are met to ensure that the series converges. In medical imaging, we often stop at the simpler terms, the constant and linear parts, because they strike a good balance between accuracy and efficiency. This idea of building up approximations using basic terms is at the heart of how we model systems practically. It lets us represent complex behavior in a form that's manageable and useful for real-world applications. Building on our discussion of the Taylor expansion, let's focus for a moment on one of the simplest and most useful forms we often work with, the linear function. For most practical purposes, linear functions give us all we need. In one dimension, this means a straight line that relates input to output. In two dimensions, we extend that idea to a plane. And in higher dimensions, the concept continues in the same way. What makes linear relationships so powerful is their simplicity. They're easy to analyze, fast to compute, and they form the backbone of much of engineering, including the systems we use for medical imaging. By relying on linear models where they're appropriate, we can create good approximations that help us understand, design, and improve imaging systems without unnecessary complexity. Now that we've seen how linear functions provide a simple and practical way to model relationships, let's extend that thinking to systems, because as engineers, that's often how we see the world. In engineering, we use mathematical operators, often written as symbols like L or O, to represent how a system transforms an input into an output. If we feed in an input signal, which we call V, the system applies its operator and produces an output, which we call W. That output shows how the system has modified or processed the input. These inputs and outputs can take many forms. They might be signals that change over time, two-dimensional images, tensors, or discrete datasets, like the pixel values in a digital image. The important thing is that the system takes something in, processes it through its internal mechanism, and produces something out. In medical imaging, this thinking applies directly to devices like CT scanners. The entire system transforms physical signals into diagnostic images that radiologists can interpret. This is where engineering and mathematics come together. We need the precision of mathematical relationships to describe what's happening inside the system, but we produce images of that precision using real-world tomographic scanners to help patients every day. Now that we've introduced the idea of systems and how they transform inputs into outputs, next let's talk about something that's essential to working with any system: measurement. As engineers, measurement is where everything starts. Without measurement, we can't analyze or control a system. It's fundamental not just to engineering but to physics as well. Think about quantum mechanics. Until we measure, we don't really know the state of a system, or the state of the system is not well defined until a measurement is made. This is the idea behind Schrödinger's famous thought experiment, where the cat is both alive and dead until measurement collapses that uncertainty into a definite outcome. In practical terms, measurement often involves comparing something unknown to a reference. For example, when we weigh an object, we place it on one side of a balance and a known standard on the other. If the balance is level, we know their weights are equal. Or in electronics, we might use a multimeter to compare an unknown resistance or voltage to a standard value. These tools give us the precision we need to work effectively. And to bring it back to systems thinking, consider this. Even something like an instructor can be seen as a system. The input is the scheduled time for class, the output is the lecture. But if something unexpected happens, like illness, the output changes. That's a reminder that a real-world system can have modifiers that influence how it behaves. After exploring how measurement is at the heart of engineering and systems thinking, let's bring that directly into the world of medical imaging. An imaging system is really a specialized type of measurement system. Take an MRI scanner as an example. Its purpose is to measure so-called K-space data and reconstruct a detailed image of a cross-section of the body. Ideally, that image would be a perfect reflection of what's inside. A sharp, clear point in the image would correspond exactly to a sharp point in the body. But of course, not all systems perform equally. A high-quality imaging system produces images that are sharp, high in contrast, and rich in detail. A low-quality system, on the other hand, might blur features, just like how a low-resolution camera gives you a softer, less precise photo. This blurring isn't just an inconvenience, it's actually a key characteristic that tells us a lot about how the system behaves. So when we think about imaging systems, sensing systems, and measurement systems, we can see that they're really in the same family. They all take in signals from the world or our bodies, process these signals, and produce outputs that we can use. Now that we've seen how imaging systems fit into the broad family of measurement systems, let's look at another important type of system, the control system. Unlike a basic measurement system, a control system doesn't stop at generating an output. What makes it special is that it uses that output as feedback to adjust its input or its own behavior. In other words, it closes the loop to achieve a desired result, even when conditions change. A good example is a radar system tracking an airplane. The radar measures the plane's position and velocity and uses that information to adjust its direction or focus, keeping the plane in view as it moves. This continuous feedback helps the system stay on target no matter how fast the plane moves. Control systems are essential in engineering whenever we need systems that can adapt, correct themselves, and maintain stability in real time. And while we don't usually think of imaging systems as control systems, these ideas come together in areas like robotic surgery for automated image-guided interventions, where feedback from imaging is used to guide robotic actions precisely. Continuing on control systems, let's comment more on robotic systems. Agentic robotic systems represent a cutting-edge area of control systems. What sets them apart is that they don't just react based on feedback. They often integrate a level of machine intelligence and have a 3D world model built in to adapt, learn, and respond to changing conditions in real time. You can observe robotic systems working in various settings. Some assist in hotels, managing tasks and interacting with guests. Others support caregivers in nursing homes. In these cases, the robots combine precise control with intelligent inference, adjusting their actions based on both the feedback they receive from their environment and the reasoning they perform according to a large AI model. This blend of control, adaptability, and intelligence opens incredible possibilities, not just in industry but in healthcare as well. We're seeing robotic systems used alongside medical imaging to guide surgeries, deliver radiotherapies, and improve patient care. After exploring robotic systems as advanced examples of engineered control systems, let's shift our focus to perhaps the most remarkable natural system, the human brain. The brain is an incredibly complex control, yet intelligent system made up of billions of interconnected neurons. These neurons process inputs from our environment, everything we see, hear, and feel, and generate intelligent actions in response. Each neuron decides whether to fire based on the signals it receives, and if so, it will pass electrical impulses that enable functions ranging from simple reflexes to sophisticated reasoning. For example, such interconnected neurons form the foundation of our physiological system. They coordinate movement, regulate vital functions, and allow us to live and adapt. And when we develop engineered systems, it's often the brain's architecture, functions, and processes that inspires us. Having just discussed the brain as an intelligent system, it's important to step back and see how it fits into the bigger picture, the human body as a whole. The body is an incredibly intricate, interconnected system. It operates across multiple levels, from genes and cells to tissues and organs, all the way up to entire physiological and psychological systems like the circulatory, respiratory, digestive, and neurological systems. These systems work together in harmony to sustain and enjoy life. When disease disrupts this balance, understanding how these parts interact becomes essential. That's where systems biomedicine come in. These fields focus on studying the body as a huge network of interacting components so that we can gain deeper insights into health, diagnose abnormalities more precisely, and develop treatments more effectively. This systems-level thinking is at the heart of modern medicine, and it aligns perfectly with how we approach medical imaging, using technology to see and understand these complex connections and coordinated actions. Let's look ahead to where this thinking is leading us. We're entering a time when the boundaries between human systems and artificial systems, like robotics and AI, are becoming increasingly blurred. Technologies such as brain-machine interfaces are already emerging. These interfaces aim to connect the brain directly with external devices, offering the potential to enhance memory, improve reasoning, and support other cognitive functions. This convergence of neuroscience and artificial intelligence represents one of the most exciting and profound frontiers in science and engineering today, which is called neuro-AI by some researchers. A closely related frontier is called agentic AI. Yet another related area is known as embodied AI. As I once heard in a talk, physics helps us understand the external world, but neuroscience helps us understand ourselves. When we bring these fields together, we're not just advancing technology, we may fundamentally reshape what it means to be human. To develop these futuristic systems, we first look at linear systems. It's important to understand the two key properties that define them: additivity and homogeneity. Let's break this down. First, additivity means that if you have two inputs, let's call them V1 of t and V2 of t, and you apply the system operator L to their sum, it's the same as applying L to each input separately and then adding the results. Second, homogeneity means that if you scale an input by some constant, say alpha, the output is scaled by that same constant. You can see the mathematical expression here. This principle is what makes linear systems so powerful. They let us break complex problems into simpler parts, solve them individually, and then combine the results. It's this property that makes linear systems both elegant and practical for engineering, and especially for medical imaging applications where we need to process or reconstruct signals in a predictable, manageable way. The bottom part shows some interesting problems. An interesting property is that if a system is linear, its output to a zero input must be zero. Also, please note that the last equation demands the condition that the infinite sum must converge. Let's now take a closer look at the first key property of linear systems, additivity. Additivity tells us that if we know how a system responds to two individual inputs, let's call them F1 and F2, then we can predict the system's response to their sum. Specifically, if input F1 produces output K1 and input F2 produces output K2, then the response to F1 plus F2 will be simply K1 plus K2. This might sound straightforward, but it's incredibly powerful. Additivity allows us to take complex inputs, break them down into simpler components, analyze each part separately, and then combine the results to understand the whole. This is one of the reasons why linear systems are so widely used, especially in medical imaging. It helps us handle complex signals and reconstruct images efficiently with precision and clarity. On the slide, you'll see this illustrated with the rotation operation, a rotation of each of input patterns of 1 and F2 and the same rotation of the sum of F1 and F2, visualizing how this principle works in practice. Following on from additivity, let's now turn to the second key property that defines a linear system, homogeneity, or what we also call the scaling property. Here's how it works. If a system produces an output K1 for an input F1, then if we scale that input, say multiply F1 by some constant factor like alpha, the output should be scaled by that same factor. So mathematically, if the input becomes alpha times F1, the output should be alpha times K1. To put this in more intuitive terms, imagine you have an image as your input. If you double the brightness of the input image, a linear system would produce an output image that is also twice as bright as the original one, no more, no less. That's homogeneity in action. When both conditions are satisfied, the system obeys what we call the superposition principle. More specifically, if two inputs are V1 and V2, giving output L of V1 and L of V2 respectively, then for a linearly combined input, alpha 1 times V1 and alpha 2 times V2, we must have the output expressed as the sum of alpha 1 times L of V1 and alpha 2 times L of V2. I will use another slide later in this lecture to review with you this important principle. The superposition principle and the set of the two properties, that is, the additivity and homogeneity, can be derived from each other. These two properties together are equivalent to the superposition principle, allowing us to predict linear system behaviors, simplify complex engineering problems, and design imaging technologies that are accurate and reliable. We've explored the two defining properties of linear systems, additivity and homogeneity. Let's put that knowledge to the test with a few examples. Here you can pause and think carefully about whether each of the given systems meets the criteria we've discussed. These small checks help reinforce your understanding. Okay, now let's discuss the answer. Suppose we have a system that maps positive numbers, x, to the square root of x. At first glance, you might notice that the output is 0 when the input is 0. That's a necessary condition for linearity, but it's not enough. To be truly linear, the system must satisfy both additivity and homogeneity. The square root function fails both tests. The square root of a sum isn't the sum of the square roots of the components, and if you scale the input, the output doesn't scale proportionally. Now compare that with something like a linear transformation in three-dimensional space, like multiplying a vector by a 3×3 matrix. This type of operation satisfies both additivity and homogeneity. It follows the superposition principle. Similarly, mathematical operations integration and differentiation both qualify as linear because they respect these two properties, additivity and homogeneity, which are the necessary and sufficient conditions. Now that we've practiced applying the definitions of linear systems through checking specific examples, let's take a moment to reflect on these properties at a deeper level and clarify subtleties out of the linear system concept. Over the years, some have wondered whether the definition of a linear system might contain redundancy. Could it be the case that additivity alone implies homogeneity, or the other way around? It's an intriguing question, because at its core, it asks us to think carefully about how we define the systems we study and the assumptions we make. This kind of exploration isn't new. Think of Euclid's geometry, which started with 5 basic postulates. Mathematicians have debated for centuries whether all of those postulates are truly independent or if some could be derived from others. In the same spirit, we can ask, are both additivity and homogeneity really necessary as separate conditions? Or could one, in some cases, imply the other? In the next few slides, we'll explore situations where these properties are independent and others where they might be redundant. Engaging with questions like what I just asked helps us build a stronger, more thoughtful foundation for engineering practice, particularly when we apply these ideas in fields like medical imaging. Since we use both additivity and homogeneity to define a linear system, we already imply that they are independent. Now, let's look at a special case where they're actually equivalent when we're dealing with continuous systems. As you can see on this slide, we're focusing on the connection between additivity and homogeneity. Let's break it down together. At the top of the slide, you'll notice the arrows that connect the two properties, additivity in the red box and homogeneity in the blue box, with the arrows going both ways. This represents the key idea. Under certain conditions, like continuity, one property can imply the other. Now look at the yellow box to support the yellow arrow. These equations show how homogeneity can be built up from additivity. We start with f of n times x equals n times f of x. This shows that if you apply the system to a scaled input, it scales the output proportionally. That's homogeneity. The next line builds on that. It rewrites f of x in terms of scaled components, showing that f of x behaves consistently under fractional scaling, using integer steps and continuity to bridge to real numbers. The last line in the yellow box shows that if f of 0 equals f of x plus f of negative x, then f of negative x equals negative f of x. This confirms the homogeneity for a real number scalar. Then in the green box, we see how additivity emerges from homogeneity. We define two inputs, x1 equals alpha 1 times x, and x2 equals alpha 2 times x, where x is not equal to 0. If we apply homogeneity, f of x1 plus x2 equals f of alpha 1 times x plus alpha 2 times, which is equals to alpha 1 plus alpha 2 times f of x. This equals alpha 1 times f of x plus alpha 2 times f of x, which equals f of x1 plus f of x2. This confirms that if homogeneity holds, we can construct additivity. So this illustrates how in continuous systems, these two properties are indeed equivalent. That is, in such cases, additivity and homogeneity aren't independent. One can imply the other. In the previous slide, we explored how additivity and homogeneity can be equivalent under certain conditions, like continuity. But here we will see that equivalence doesn't always hold. Let's break it down. This example focuses on the complex conjugate operation. The system is defined as f of z equals z star, where z equals x plus iy. Taking the conjugate of z flips the sign of the imaginary part, so f of z equals a minus ib. Let's look at additivity first. The slide shows f of z1 plus z2 equals the conjugate of z1 plus z2, which equals z1 star plus z2 star, and that equals f of z1 plus f of z2. This means the system satisfies additivity. The conjugate of a sum is the sum of the conjugates. Now consider homogeneity. F of alpha z equals the conjugate of alpha z. For a complex scalar alpha, this equals alpha star times z star, which is not the same as alpha times f of z, unless alpha is purely real. So homogeneity fails when the scalar is complex. This is a great example that demonstrates why we can't assume additivity implies homogeneity. We really do need to verify both conditions when testing for linearity. Finding a counterexample like this for real scalars remains an open question, where thoughtful reasoning is still welcome. If you figure it out, please let me know. On the previous slide, we saw how additivity doesn't necessarily imply homogeneity. Now let's look at the reverse, a case where homogeneity holds but additivity fails. This slide presents a clever example. We define a real-valued function where f of x equals m1 times x if x is rational, and f of x equals m2 times x if x is irrational, where m1 and m2 are rational constants, and importantly, m1 is not equal to m2. Since we're only scaling inputs by rational numbers in this example, the homogeneity property holds. That's because multiplying by a rational scalar doesn't change whether the input is rational or irrational, so the function scales consistently. But here's how additivity breaks down. If we add two irrational numbers, x1 and x2, whose sum happens to be rational, the function behaves differently on the sum compared to the sum of the individual function values. Specifically, we have f of x1 plus x2 equals m1 times the sum x1 plus x2, but f of x1 plus f of x2 equals m2 times x1 plus m2 times x2. And since m1 is not equal to m2, these two expressions are not equal. This example demonstrates clearly that homogeneity doesn't guarantee additivity. Both properties are essential and independent when defining a linear system in a general case. That is, both the properties are indeed needed. Now that we've explored examples showing how additivity and homogeneity can be independent or dependent, let's bring it all together with a recap. A linear operator is defined by a criterion that combines additivity and homogeneity into a single expression. An operator L is called linear for a particular class of inputs V and a scalar in a given domain if and only if it satisfies the superposition principle. We can express this defining property with the following equation. L of alpha 1 times V1 of x plus alpha 2 times V2 of x equals alpha 1 times L of V1 of x plus alpha 2 times L of V2 of x. What this means is simple but powerful. If you combine two inputs and scale them, applying the system operator to that combination gives the same result as applying the operator to each input separately, scaling the outputs and adding them up. The predictability they offer allows us to break down complex signals, analyze them efficiently, apply tools like Fourier analysis or convolution, and do so with confidence. And remember, as shown at the bottom of the slide, a linear system is simply a system described by a linear operator. This foundational idea paves the way for everything that follows, including how we approximate nonlinear systems as piecewise linear, and how we build advanced imaging technologies on these principles. Now let's explore an important refinement, relative linearity, which is not in any textbook. On an earlier slide, I mentioned an interesting property of a linear system. That is, if a system is linear, its output to a zero input must be zero. However, if a function is linear, its value for input x can be non-zero. How do we reconcile this apparent discrepancy between the concept of a linear system and a linear function? Clearly, the inconsistency comes from how we define the baseline. We can resolve this by focusing on relative changes rather than absolute values. What do I mean? Imagine a system where the input-output relationship is tied to a specific coordinate system or reference point. Instead of looking at the absolute input and output values, we examine how changes in input produce changes in output. This approach allows us to apply linear system theory even when the system's baseline isn't aligned with the origin. On the slide, you see this idea expressed mathematically. We define delta y1 of t equals L applied to delta x1 of t, and delta y2 of t equals L applied to delta x2 of t. This is the system's response to changes in input. Then, if the superposition principle applies to these changes, that is, alpha times delta y1 of t plus beta times delta y2 of t equals L applied to alpha delta x1 of t plus beta delta x2 of t, we call the system linear. This shows that by focusing on relative changes, the system behaves linearly, even if the original absolute function looked nonlinear because of an offset or intercept. This concept is especially useful in medical imaging, where systems often operate around a baseline or reference signal, and what matters most is the change we're trying to detect or measure. Now that we've explored abstract concepts like linear operators and relative linearity, let's ground that understanding with a familiar, real-world example, the resistor. This slide shows the classic voltage-current or V1 relationship for a resistor, referred to as Ohm's law. You can see the simple equation, V equals IR, where V is voltage, I is current, and R is resistance. If we rearrange that, we get I equals V divided by R. What's important here is that this is a linear relationship. If we double the current through the resistor, the voltage doubles too. Similarly, if we double the voltage, the current doubles. The proportionality is direct and consistent. This is a hallmark of a linear system. And as shown on the slide, no matter which form of the equation we use, whether voltage as a function of current or current as a function of voltage, the linearity remains clear. This simple V1 relationship is a perfect example of linearity in action. Let's now explore another essential electrical component, the capacitor, which is also a linear system. Capacitors are widely used in imaging equipment from ultrasound devices to MRI systems because of their ability to store and release electrical energy. On this slide, we see a diagram of a capacitor. It consists of two conductive plates labeled as plate A and plate B, separated by a dielectric material. We see that this structure combines multiple mini-capacitors into one unit, which increases the overall capacitance. This kind of design is common in medical imaging hardware where compact, reliable energy storage is vital. Now, let's focus on the voltage-current or VY relationship that defines how a capacitor behaves in an electrical circuit. We have the mathematical expression for this relationship showing that the voltage across the capacitor depends on the integral of the current over time. In simple terms, the voltage builds up as current flows into the capacitor and accumulates electrical charges. Conversely, the current through the capacitor is proportional to how quickly the voltage changes over time. This characteristic makes capacitors essential for shaping and filtering signals in medical imaging devices. For example, capacitors help stabilize power supplies and smooth out analog signals before they are converted into digital data in imaging systems like CT or MRI scanners. They are one of the many components that ensure medical imaging equipment operates well, supporting the reliable capture of diagnostic images. Let's now turn our attention to another key electrical component, the inductor, which can also be modeled as a linear system. We see a diagram of an inductor, which is made of a coiled wire that generates a magnetic field when current flows through it. The magnetic field lines, shown here, represent how energy is stored in the magnetic field of the inductor. When it comes to the voltage-current relationship, the inductor behaves a little differently from the capacitor. We see on the slide that the voltage across the inductor depends on how quickly the current is changing over time. This means that inductors resist sudden changes in current, helping smooth and stabilize electrical signals. Conversely, we also see that the current through the inductor depends on the integral of the voltage over time. So as voltage is applied, the current builds up gradually rather than changing instantly. This behavior makes inductors valuable in medical imaging systems for filtering signals and for managing electromagnetic interference, especially in sensitive equipment like MRI machines. Together with capacitors, inductors help ensure that imaging devices produce critical diagnostic information. As we unwrap the foundation of medical imaging, let's look at an important concept that helps explain how imaging systems work reliably, the shift-invariant linear system. We see on this slide that a shift-invariant system has a special property. If the input signal shifts in time, the output shifts in the same way. In simple terms, the system's response is predictable in a simplistic way. No matter when or where the input happens, the output will occur correspondingly. For example, imagine I take a picture of you here in this room and then I take your picture again in my office. If my camera is shift invariant, your image should look the same in both cases. The system responds consistently even though your location is shifted. This kind of stability is essential for medical imaging systems where we want clear, reliable results, whether we're imaging a patient in this or that imaging center. Mathematically speaking, when the input signal is V of t, the system produces an output W of t. And when the input shifts to V of t minus tau, the output shifts in the same way, becoming W of t minus tau. This property supports the mathematical tools we'll use, like convolution and Fourier analysis, which are key to understanding how images are formed and processed in modern medical imaging. Continuing from our discussion of shift invariance, let's look at another way to think about this important concept. Imagine dropping a stone into a still pond. Ripples spread out from the point where the stone lands. Now, if you drop another stone at a different spot, what happens? We see the same ripple pattern, but this time it's simply shifted to match the new location where the second stone landed. The system, the pond in this case, responds in the consistent way, corresponding to where the input is. This is a great way to visualize spatial invariance in a system. Just like with those ripples, a shift-invariant linear system in medical imaging ensures that the system's response stays consistent when the input changes position. This property helps imaging systems deliver repeatable and easily interpretable results, whether we're scanning different parts of the body or dealing with shifts in the patient's position. Continuing our exploration of shift-invariant systems, let's look at another example showing how this idea applies over time. Like our earlier example with spatial invariance, think of a music player. Whether you play your favorite song today, next week, or even a month from now, the melody and rhythm sound the same. The system, the music player, produces the same output, just at a different point in time. This consistency is what we call shift invariance in the time domain, or temporal invariance, or time invariance. The system's response doesn't depend on when the input occurs. Instead, it remains predictable and reproducible over time. As a review of the shift invariability concept, let us summarize this property mathematically and visually. Mathematically, shift invariance means that if the input shifts by some amount, let's say by a distance or time value a, then the output shifts by exactly the same amount. We can visualize this clearly on the slide. The top example shows an input signal applied to the system, and then the system produces a certain output. When that input shifts, shown as f of x minus a, the output shifts in the same way, becoming g of x minus a. The system's operation stays consistent no matter where or when the input occurs. As mentioned earlier, this property is desirable and helps ensure that our imaging systems respond in a highly reproducible fashion, whether we're scanning different parts of the body or performing scans at different times. Let's finish our discussion on linear systems by touching briefly on nonlinear systems. You'll notice the green button on this slide. This signals that this topic is good to know but not required in the exams of this course. Nonlinear science is a highly complex field. Unlike linear systems, where solutions can often be relatively easily found through analytic or numerical calculations, nonlinear equations are typically much harder to solve. In many cases, it's impossible to find exact solutions. But thanks to modern computing, we can break these equations down into smaller parts and solve them numerically, even if it sometimes takes significant computing power to do so. What makes nonlinear systems particularly fascinating is that they can produce surprising, often counterintuitive behaviors. We give examples here like chaos, solitons, and singularities. These are patterns or events that seem unpredictable or puzzling at first glance. And naturally, anything that challenges our intuition tends to spark curiosity and deeper investigation. One famous example of a nonlinear system that we give here is the logistic map. This is a simple but powerful mathematical model that helps explain how a population, such as a group of rabbits, can change over time. Let's take a look at the equation on this slide. It shows that the population at the next step depends on two things: the population at the current step and a growth rate factor, r. At the first glance, the equation looks straightforward. But because it includes a nonlinear term, the population multiplied by 1 minus the population, the system's behavior can change dramatically depending on the value of r. When the population is small, growth is nearly linear and predictable. But as the population grows and starts to approach the full capability of its environment, growth slows down since resources become scarce. As a result, the population may stabilize or decline. This simple model reflects how nature regulates itself and how complex patterns like stability or even chaos can emerge from such a simple non-linear system. How could the logistic map reveal something truly fascinating? Let me explain further to understand so-called chaotic behaviors. We give this example where the population's growth is simulated in MATLAB. The code on the left sets up the calculation, and on the right we observe the results plotted in what's called a bifurcation diagram. What's remarkable is how the system's behavior changes as the growth rate increases along the horizontal axis. At low growth rates, the population, represented by the vertical axis, settles into a single stable value. As the growth rate rises, the population begins to oscillate between two values, then 4, then many. Eventually, it enters a state where the behavior appears random and unpredictable. This is what we call chaotic behavior. It's important to note that this is chaos in a mathematical sense. The system is fully deterministic, its behavior is governed by precise rules. But because it is so sensitive to initial conditions, small changes at the start can lead to dramatically different outcomes. This example shows the same principle that helps explain why long-term weather forecasts can be unreliable. While this idea doesn't directly tie to quantum mechanics, it reminds us that even in systems ruled by clear equations, the results can seem random when non-linear dynamics are involved. Let me give you another fascinating example of a non-linear system, the biological neuron. We can see here how a neuron collects signals through its branches called dendrites. These inputs are processed by the cell body or soma. Small signals on their own have no effect on the cell status, but when the combined inputs reach a certain threshold, the neuron fires. The activated neuron sends an electrical impulse down the axon, ultimately reaching the synapse, where it communicates with the next cell. This thresholding behavior helps the nervous system filter out noise and respond only to meaningful stimuli. Just below the cartoon of a biological neuron, we see how a biological neuron is mathematically modeled using an artificial neuron. Here the inputs are linearly combined into a weighted sum. That's the linear part of the artificial neuron. Then this sum is passed through a nonlinear transformation that decides whether the neuron should fire. This simple structure forms the basic building block of artificial neural networks, which are widely used in modern artificial intelligence research and increasingly in medical imaging tasks like image classification and image reconstruction. Let's take a look at what happens when we connect artificial neurons in layers. When we do this, we create a neural network. And when we stack many of these layers together, we build what's called a deep neural network, or DNN. This structure forms the foundation of modern deep learning, the mainstream field of AI and machine learning. Here we observe how deep neural networks learn in a hierarchical way. We see in the diagram that the lower layers are responsible for detecting simple features, things like edges, corners, or basic textures. As we move deeper into the network, the layers begin to recognize more complex patterns like parts of faces and finally an entire face. This layered learning allows deep neural networks to solve real-world problems. Today they are used in technologies ranging from facial recognition to self-driving cars and increasingly in medical imaging. For example, detect subtle clinical features that might not be obvious to the human eye. It's a powerful example of how integrating artificial neurons as basic computing elements can help us tackle challenges that were once thought to be beyond the reach of computers. As we wrap up this lecture, let me encourage those of you who are particularly motivated to consider pursuing a class project. This would be in addition to the exams and homework assignments that are integral part of the course. For potential class projects, let me suggest an exciting direction. Combining machine learning with medical imaging, a fast-growing area that offers incredible opportunities for innovation. If you're curious about this topic, I recommend reading my perspective article shown on the slide, which is the first roadmap for the emerging field of AI-based tomographic imaging. It discusses how AI, deep learning, and tomographic imaging can come together to create new algorithms for image reconstruction and analysis. This is an area where breakthroughs are happening, and your project could be a chance to do cutting-edge medical imaging research and potentially produce publishable results. If a project doesn't interest you, that's perfectly fine. You can focus on the regular course materials, including lectures, homework assignments, and exams. I'll upload today's homework assignment to our LMS system for you to download. Please submit your solutions within 1 week. After the deadline, we'll post the answers for your review. Thank you for your attention today.